November 9, 1965. Near Niagara Falls, one backup relay trips a perfectly healthy line. Within seconds, 4 more lines follow. Within minutes, 30 million people are in the dark. So, how does a healthy grid tear itself apart in minutes? The answer is called transient stability, because that night, nothing physical had failed. No fallen tower, no burned-out plant. What broke was invisible. Every generator on the continent spins in a shared rhythm, and a big enough shock can knock them out of step, all of them at once. The tool that predicts it is a single line of physics, the swing equation. Newton's second law, written for the grid. So here is the plan. First, the invisible rhythm that locks every generator in step. Second, we build the swing equation, term by term. Third, a fault hits, and we watch a rotor swing, degree by degree, against a deadline. And finally, back to 1965, to see what the equation says the grid should have done. Start with the rhythm. Every generator on the grid spins at exactly the same electrical speed. This lockstep is called synchronism. The magnetic field inside each machine works like a spring, tying the spinning rotor to the grid. Push more steam through the turbine, and the rotor does not spin faster. It edges slightly ahead, and the spring stretches. That stretch has a name: the rotor angle, delta. It is the angle between the rotor's position and the grid's rhythm, and it sets the power. The power a machine sends out follows the sine of delta. Stretch further, send more, up to a hard ceiling. Our machine today delivers 1 per unit with a ceiling of 2, so it rests at an angle of 30 degrees. Remember that number, because the turbine never stops pushing, and in 1/10 of a second, that spring is about to be cut loose. Now the equation. A rotor is a spinning mass, so it obeys Newton's second law for rotation. Unbalanced power makes the angle accelerate. On one side, the mechanical power the turbine pushes in. On the other, the electrical power the grid pulls out. When they balance, the angle holds still. When they do not, the difference pours into the rotor's motion and delta starts to move. The rotor's resistance to that change is its inertia. Engineers wrap it into one number, h, the kinetic energy stored in the spin divided by the machine's rating. It is measured in seconds, usually between 2 and 9. An h of 5 means the stored spin alone could feed the machine's full output for 5 seconds. From h comes the acceleration constant in the equation, m, on screen here. Keep it in view, because we are about to divide by it. Lightning strikes a line just outside the plant, a 3-phase fault, the worst kind. The voltage at the machine collapses, and with it, the electrical power. The grid can no longer pull energy out. But the steam turbine does not know there is a fault. It keeps pushing 1 full per unit of power in. That surplus has exactly one place to go, into the spin of a rotor that weighs hundreds of tons. The swing equation says the angle now accelerates at over 2,000 degrees per second squared. Pause here and try it yourself. Starting from 30 degrees, how far does the rotor swing in just 1/10 of a second? Here is the answer, about 11 degrees. From 30 to nearly 41, 1/10 of a second, 11 degrees. This is the whole game of transient stability. The fault must be cleared before the angle runs too far. Every cycle the breaker saves is degrees the rotor never gains. At 0.1 seconds, our breaker finally opens. Now comes the real question. Is it too late? The fault is gone, but the rotor is still moving too fast. The angle keeps climbing past 41 degrees. Now though, the grid is back, pulling power out. And above 30 degrees, it pulls out more than the turbine puts in. The rotor starts to break. 2 futures are possible. In the first, the braking wins. The angle peaks, swings back, overshoots a little, and settles into a calm oscillation around 30 degrees. That is a stable swing. The grid rides through. In the second, the fault lasted a little too long. The angle sails past 90 degrees, where the braking begins to fade instead of grow. the rotor tears loose from the grid's rhythm. That is loss of synchronism, a pole slip. Inside the machine, it means brutal torque reversals hammering a shaft the size of a tree trunk, so protection must trip the unit instantly. One machine gone, and every machine left behind now carries its share. Now we can read 1965 properly. When those 5 lines near Niagara opened, well over 1,000 megawatts had to find new paths instantly. Machines that had been resting at comfortable angles were suddenly pushed toward their limits. Across Ontario and the Northeast, rotors began to swing against each other, exactly like our single machine, but hundreds of them at once. Within seconds, groups of generators tore out of step. Protection did its job and split the grid into islands to save the machines, but most islands could not balance load against generation, and they collapsed one after another. 30 million people, up to 13 hours. Not one tower had fallen. The blackout was a transient stability event, the swing equation playing out at continental scale, and it changed the industry. It gave us NERC, stricter relay rules, and stability studies that now run before every planning decision. Today, engineers solve this equation for thousands of possible faults every year, so that one relay tripping on a healthy evening can never again take a continent with it. So, here is the whole story in 4 lines. Every generator holds a rotor angle, delta, and its power follows the sine of that angle. The swing equation is Newton's law for that angle. Surplus power makes it accelerate. A fault removes the braking. The angle runs, and the clearing time decides whether the machine swings back or tears loose. And inertia, H, buys the time that makes everything else possible. Next time, a shortcut that feels like magic. Finding the exact clearing deadline with nothing but 2 shaded areas on a graph. No differential equation required. Until then, a question for you. If H doubles, what happens to that first swing? Tell us below and subscribe so you do not miss the answer.